Welcome to part 4 of this series. In this video we will discuss some of the major behaviours of the ocean and how they impact climate change. The ocean covers 71% of the Earth's surface and contains 97% of the planet's water. It therefore seems self-evident that it must have a large part to play in the climate. Now, this common sense assumption is confirmed by the IPCC in its September 2013 report, which makes the following statements regarding the oceans. The ocean influences climate by storing and transporting large amounts of heat, fresh water and carbon, and by exchanging these properties with the atmosphere. About 93% of the excess heat energy stored by the Earth over the last 50 years is found in the ocean. Chapter 3, paragraph 3.1 of the report. Another quote: "Ocean warming dominates the increase in energy stored in the climate system, accounting for more than 90% of the energy accumulated between 1971 and 2010. This is section B2, the heading. And a final quote of several. "More than 60% of the net energy increase in the climate system is stored in the upper ocean between 0 to 700 metres during the relatively well-sampled 40-year period from 1971 to 2010, and about 30% is stored in the ocean below 700 metres. This is section B2, paragraph 3. The oceans interact with the climate in numerous ways, including heat absorption, heat conveyance, and evaporation. In this video, we will concentrate on the movements of water within the oceans. The oceans circulate and swirl in constant dynamic movement and in immensely complex and interacting ways. To get a better understanding of this complexity and how it could be connected to climate change, climate scientists have tried to break down and classify the overall behaviour of the oceans into sets of sub-behaviours. The first behaviour we will look at is the global ocean conveyor belt. This is a constant and long-term movement of the ocean. The movement is due to thermohaline currents, where thermo refers to temperature and haline refers to salt or salinity. This motion comes about because of two quite simple properties. Property 1, cold, salty water is dense and therefore sinks to the bottom of the ocean. Property 2, warm, salty water is less dense and hence rises to the surface. From the diagram you can see that the ocean conveyor gets its start in the Norwegian Sea, where warm water from the Gulf Stream heats the atmosphere in the cold northern latitudes. This loss of heat to the atmosphere makes the water cooler and denser. And because of property 1, the dense water sinks to the bottom of the ocean. As this continues and more warm water is transported north, the cooler water continues to sink and is forced to move to the south to make room for the incoming warm water. Eventually, as the diagram shows, this cold bottom water flows from the North Atlantic to the south of the equator, all the way down to Antarctica. From here they bring cold temperatures into the Pacific. But the journey into the Pacific gradually warms the water so that it becomes less dense, so the cold bottom waters rise to the surface. and pass through the Indian Ocean as a warm stream that continues onto the start point in the Norwegian Sea. It takes almost 1,000 years for the conveyor belt to complete one full oscillation. The Oceanic conveyor belt is especially important to Northern Europe as it transports heat northward via the Gulf Stream and North Atlantic Current, and thus contributes to the Northern Hemisphere's moderate climate. Now, given that it takes 1,000 years to complete a cycle, it might be interesting to look back 1,000 years to try to establish correlations between this ocean behaviour and climate fluctuations over that time. If we do this, we would go back to around 1020, 1010. So what were global temperatures at around 1020? Well, this was during the medieval warm period, which occurred, according to the IPCC definition, as between 950 to 1250. So coincidentally or not, the planet was in the midst of a warm period then, just as now. Now, I don't want to make too much of that possible coincidence at this moment. So let's move on to the next behaviour of the ocean, which is the ENSO. The ENSO stands for the El Nino Southern Oscillation. ENSO refers to the oscillation of first warming and then cooling waters back and forth across the Pacific, much like the water in a bathtub. Now, ENSO is a collective term. Its components are El Niño and La Niña. El Niño and La Niña are effectively the opposite phases of this oscillation. The El Niño phase involves the spreading of seawater, which is warmer than normal, across the equatorial Pacific, while the La Niña phase is the spreading of cooler than normal water over the same region. This diagram shows a normal state of the regions concerned. Points to note are the strong trade winds blowing from the east, the strong Peruvian current spreading cool water along the coast of Ecuador and Peru, and the warm water above Australia. During an El Niño event, however, the trade winds weaken, as does the Peruvian current. This enables an eastward migration of warm water onto and along the coasts of Ecuador and Peru. This phenomenon got its name as it mainly occurs around Christmas and was given the Spanish name of El Niño, meaning the Christ child. It can have a profound and disruptive impact on the fishing economies of Ecuador and Peru. Birds, sea lions, fishermen, their family go hungry because there are not enough fish to go around. In terms of the local climate, the offshore warming effect of El Niño causes torrential rainfall in the coastal zone, which frequently leads to severe flooding. During a La Niña event, the trade winds that blow from the east become stronger. This counteracts the eastward migration of warm water that occurs in El Niño. And instead, cold waters force themselves along the equator and west coast of South America, where now, instead of the El Niño warm water, cold waters flow onto and along the coasts of Ecuador and Peru. During this La Niña behaviour, sea surface temperatures along the equator can fall by as much as 7 degrees Fahrenheit below normal. El Niño and La Niña episodes typically last 9 to 12 months, but some prolonged events may last for years. They often begin to form between June and August, reach peak strength between December and April, and then decay between May and July of the following year. In the literature, it is often generalized that El Niño and La Niña events typically occur about every 3 to 5 years, and that El Niño events usually occur more frequently than La Niña. But as this chart shows, it is quite difficult to generalize like this in an accurate way. The chart also shows how difficult it would be to try to predict El Niño and La Niña events, both in terms of their duration and their periodicity. It is also important to note that the effects of these oscillations are not confined to Peru and Ecuador. They can have large-scale, short-term impacts, not only on ocean processes, but also on global weather and the temperature. For example, during La Niña episodes, the waters near Australia are often 5 feet higher than the ocean surface in the east. As another example, during the transition from El Niño 1997-1998 to La Niña 1998 to 1999, mean summer ocean temperatures off the coast of Oregon decreased by 2 degrees beginning in 1999. More than this, temperatures at some locations off the California coast fell by nearly 18 degrees Fahrenheit between 1998 and 1999. This graph plots ENSO cycles against global temperature. It shows the correlation between the ENSO cycles and short-term global temperature fluctuations. There are, I think, strong correlations, which we will return to during the summary at the end of this video, and importantly, in the next and final part of this series. We will now look at another oscillation that occurs in the oceans, the PDO, the Pacific Decadal Oscillation. The PDO is similar to the ENSO in character, but the PDO takes place, as the name implies, over decades. The PDO can remain in the same phase for 20 to 30 years, while ENSO cycles typically last 6 to 18 months. The PDO, like ENSO, consists of a warm and a cool phase. The behaviours and impacts of the PDO can also interact with the ENSO behaviours and impacts. We will follow up on the interaction between the ENSO and PDO a little later, but first, let's look at the PDO itself. This diagram shows the classic features of a warm PDO. You can see a broad area of above average water temperatures off the coast of North America. Now, these warm waters stretch from Alaska to the equator, and they wrap in a horseshoe shape around a core of cooler than average water. Turning to a cold PDO, this is pretty much the opposite of the warm PDO. From the diagram, you can see the area of below average water temperatures off the coast of North America from Alaska to the equator. Now, these cold waters form a horseshoe around the area of warmer than average sea surface temperatures. in the central Pacific. Almost the exact opposite, if you like, of the warm PDO. Shifts in the PDO phase can have significant and widespread implications for global climate. It can affect Pacific and Atlantic hurricane activity. It can affect droughts and flooding around the Pacific basin. It affects the productivity of marine ecosystems as well as global land temperatures. It also affects the Indian summer monsoon. Additionally, some climate experts believe that the PDO can intensify or diminish the impacts of the ENSO according to its phase. We referred to this earlier. Now, if both ENSO and the PDO are in the same phase, that is, either both warm or both cold, then it is believed that El Niño and La Niña impacts may be magnified. Conversely, if ENSO and the PDO are out of phase, it has been proposed that they may offset one another, preventing normal ENSO impacts from occurring. This chart presents a time series of shifts in the sign of the PDO from 1925 to present times. Values are averaged over the months of May through September. Red bars indicate positive or warm years. Blue bars indicate negative or cool years. Given the global effects of the PDO, it is interesting to compare PDO cycles from 1930 to present times to the rise of global temperatures over that period. Now, in the first part of this series, I noted that from around 1930 to 1940, the global temperature rose significantly. This has a medium correspondence to a warm PDO period, as you can see. There is an offset that does continue past 1940 for about 7 years. In the first series, I then said that from around 1940 to 1975, there was no further rise in global temperature. There even looks to have been a slight drop. Now, this has a strong correlation with the PDO cold phase. And from around 1975 to 2000, there was a sustained upwards trend in global temperature. There is again a strong correlation with the PDO warm phase. One last point, 2008 and 2012 were the most negative values on record since 1956. Now, this period also corresponds to a slowing down of the global temperature rate of increase. Before concluding this video, we should understand that there are significant oceanic circulations that we have not discussed. To discuss them all would extend this video to several hours, if not days. But I think it will be beneficial to mention one more, particularly as this occurs in the Atlantic Ocean. So I will briefly turn our attention to the AMOC, which stands for the Atlantic Meridional Overturning Circulation. The AMOC is similar in some respects to our first subject, the global ocean conveyor belt. But the behaviour is confined to the Atlantic, and importantly, it takes place over decades as opposed to 1,000 years. The AMOC behaviour is once more caused by warm water rising to the surface and cold water sinking. The diagram shows a warm northward flow of warm water. These warm waters stretch from the surface of the ocean down to an approximate depth of 1,200 metres. The northward flow of warm water is compensated by a southward return flow consisting of lower currents of colder and denser waters. These flows, at depths of between 1,200 metres and 5,000 metres. And just like the long-term conveyor belt, but over short time frames, the AMOC transfers heat from the ocean to the atmosphere. This contributes significantly to the temperate climate of northwest Europe. So, to summarise this video, we have seen that the behaviours of the oceans are immensely complex and that they follow cycles. And cycles of ocean behaviour do correlate to fluctuations in the global temperature. Sometimes the correlation is strong, sometimes the correlation is weaker. Building on this, and to give a focus to the final part of this series, I would like to put forward a proposition that I will challenge and debate in the next video. The proposition is: the warming of the planet since 1850 can be explained by the fact that the planet was emerging from a cold period, the Little Ice Age, and by the natural causes we have discussed in the first 4 parts of this series. Man-made causes are not necessary to explain the warming. Now, the counter to this proposal would be to say something along these lines. Yes, natural events have contributed to global warming, but man-made causes, and in particular carbon dioxide emissions, have accelerated the warming to a dangerous rate. So to take up the debate in the next and last part of this series, we will examine the role of greenhouse gases and carbon dioxide in particular. We will attempt to draw together some themes and correlations based on all the series. And in doing this, we will often refer to the IPCC 2013 report and to the follow-up AR5 report published in April 2014. We will go on to examine climate models and their efficacy at predicting the future. For this latter point on climate models, I will enlist the help of Lord Bernard Russell. For those of you who are unfamiliar with him, he was a British philosopher, logician, mathematician, historian, and social critic. Some of his insights will be useful to us and will hopefully add weight to my opinions. I will leave you with one of his quotes, which should help us conduct a rational and objective debate, if we take the quote to heart. The whole problem with the world is that fools and fanatics are always so certain of themselves, and wiser people so full of doubts. I hope to see you in the last part of the series.